What's up? What's up? This is the Cyber Tutor. So today we are beginning this course on binary analysis, which is a very important topic for things like exploit development, where you are trying to hunt for vulnerabilities inside of binaries or inside of executable programs. So this course is meant to be sort of a top-down overview on how to do that. This is also good for things like learning disassembly, reverse engineering, all of that sort of awesome stuff. So the first thing I want to do is talk about the book that we'll be using for the course. So the book is Practical Binary Analysis by Dennis Andriesse. I hope I didn't butcher that guy's name. If I did, I'm so sorry. This came out in about 2018, but it's still a really good source for being able to analyze binary programs. And so I'll be following along with the book. Occasionally I'll be quoting things from the book because I feel like the book can explain better with certain definitions than I ever could, honestly. So I'm going to be doing that as well. So if you want to follow along with me, the first section that I'll be using is actually not chapter 1, so I'm jumping straight to the appendix. So Appendix A is what I want to start with, because I feel like that would be the best place to begin, because that is called a crash course on x86 assembly. So I want to start with that. I think it would be a really good overview, and also I think it would be good for you guys, obviously, to see kind of where you are with assembly language. If you get stuck on anything, there are a lot of good resources that I can put in the description that can kind of explain more about basic assembly and how all of that works. So, okay, so I think I will begin. So the language that we'll be using is the x86 instruction set. So when we say x86, that refers to the 16-bit, the 32-bit, and the 64-bit. So if you've ever seen x86_64, you might think that that's different. We're going to use x86 as kind of a catch-all to encompass all of that. So all of these are using the Intel syntax, not the AT&T. We'll talk a little bit more about that later. So this is x86 Intel assembly language. So the first thing we're going to do is look at this basic assembly program that came with the book. And mine is a little bit different than the one that's in the book because I compiled the code myself on my own machine on Linux, on Kali. So I want to just cat out. Let's take a look at this program first. So this is just a very, very extremely simple C program. I don't know if you've seen C before, if you've ever worked with it or written it, but you'll know that it can get very complicated very fast. The best thing to do to analyze, I think, assembly language is to just create these like little programs that don't really do a lot. Get it down to like the bare bones and then take a look at it and try to figure out what it does. You can even throw it into like an AI, like ChatGPT or Claude or something like that, and just say, hey, break this down for me. What does this assembly do? So if we want to get the assembly language out of this program, we want to compile it, but we don't want to go through the entire process of compilation, which is compiling, assembling, and linking. So there are 3 parts to that. We just want to compile it into the assembly and then have it do nothing else, just so that we can get that assembly output and we're actually able to see the assembly instructions. So if we want to do that, we can do the GNU compiler and then do -s and then hello world.s. .c. So this should output hello world.s, which would be the assembly instructions. So .s signifies assembly instructions that have not been assembled and linked. So let's cat that out. Hello world.s. Okay, great. So we've got a lot of stuff going on in here, and as you can tell, the program significantly expanded in meaning that it became more verbose. So you've got this very simple program here in C. Thank God we have programming languages, so we don't have to make super sophisticated programs using this, because that's what people used to do in the past. But programs very quickly got very complicated, and we realized that we needed something to help out with that. So here we've got some very basic sort of parts to this assembly program. The first one would be an instruction. So an instruction is something like this. This says push Q, RBP. You don't have to worry about what RBP is. That's a register, but don't worry about it just for the time being. So an instruction, I'm going to read from the book here because I think it has a good definition. Instructions are the actual operations that the CPU executes. So this is doing something, right? And you'll notice that it doesn't have a little dot in front of it. It just says do something and then do it with this. Or in this case, you would say do something else. This is sub Q. And then do that with this and with this. So you don't have to worry about what those are yet. So then we have something called a directive. So a directive is a command that tells the assembler to produce a particular piece of data, place instructions or data in a particular section, and so on. So a directive would be something like this, right here with a dot in front of it. You can always tell what a directive is because it's got a dot in front of it. So that's not an instruction. That's actually just talking to the assembler itself. It's basically telling it to create a piece of data or put some data in a certain section or something like that. So it's not actually executing an instruction on the CPU. And then you have labels. So labels are symbolic names that you can use to refer to instructions or data in the assembly program. So that would be something like this, .lc0. This is a label that's been created for this value here, for this string. So I think that they just generate sort of on their own. And then you have comments. So there's no comments in this, but if we did have comments, it would look something like this. You use a semicolon first, and then you just say comment. So those are human readable strings for documentation purposes. Okay, so now we want to talk a little bit about what is kind of in these sections here. So first we have section RO data. If you see this here. So this is a section dedicated to storing constant data. The directive .section tells the assembler in which section to place the following content, while .string is a directive that allows you to define an ASCII string. So it's basically saying, okay, in RO data, put this string hello world. The main function is in the text section. So you can see here we switch to text. This is a directive that sets main as global, which is a different thing you don't have to worry about. It declares main as a function. So .type, it changes its type to a function. And then we have main. So main is given a label. And then we actually get here, we get the instructions within main, which is a function. So when you're programming, right, you always, well, for the most part, you declare main. So right here. So this is how it's translating, as you can see, to the assembly language. Okay, so another thing that we want to take note of is, hold on a second. Another thing we want to take note of is that if you see here, there's a call. So when you have a call, it's calling another function. And here it's interesting because when we cat out our original program, hello world.c, you can see that we did printf. But in this assembly version of it, the compiler changed it to puts, which is kind of a similar function, pretty much effectively does the same thing. But what's interesting is that it actually simplified it for us. So it took printf and it simplified it, and then it changed it to puts, because it figured, well, I can do the same thing, I can simplify it. I don't need as many, instructions to do that, so I'll just do that. So that's exactly what it did. So next what we want to do is we want to convert this actually to Intel syntax, because right now it's in something called AT&T syntax. So AT&T syntax and Intel syntax are similar, except the order of operations is different. So for example, if you've got like a move command and you want to move a value A into B, that's how you would do it in the AT&T syntax. But in the Intel syntax, you actually do it backwards. So you'd say move B, move into B, A. So that's the main difference between those two. The way that you can tell the difference also is that if you've got these dollar signs and these like percentage signs floating around, that's how you know you're in AT&T syntax, because the Intel syntax isn't going to have those. So the way that we can change this to the Intel syntax is that we want to compile it with gcc-s masm equals Intel. So this tells us that we want the assembly language to be Intel. And then we can go back and we can do hello world.c, and it should replace that now with the correct assembly language syntax. So let's cat out hello world.s. Awesome. Okay, so now you can see the difference, right? So no more dollar signs, no more percentage signs. We've just got the syntax here. And so again, in AT&T, you move A into B. In Intel, you move A into B like that. Okay, so now we want to talk about the machine level structure of x86 instructions. So x86 instructions can actually go all the way up to 15 bytes, which is a lot, you would think. So traditionally, we're kind of used to, when we talk about x86, thinking about shorter instructions, but we can actually go up to 15 bytes on some of these. So those would be multi-byte instructions generally. A lot of 86 instructions also consist of only 1 byte. Usually those are kind of the older instructions, the OG instructions, if you will. But yeah, so also these instructions can start at literally any memory address. The CPU does not distinguish between memory addresses. However, compilers do align code to optimize the performance of fetching instructions from memory.